Okay, so previously we modified the program so that we could calculate, solve Schrodinger's equation for a molecule, and the bond length of that molecule we just set as our x max. So we have an atom on this side and an atom on this side. We can change the distance between the nuclei, and you can watch the wave function evolve, and the energy levels shift. So as you make that bond, the energy goes down. What we're going to do here is we're going to make a button that will automatically scan from a bond length of something very small to some distance where the bond will have broken. Save the eigenvalue at each step, and thus generate a potential energy surface for that molecule, from which you can see the equilibrium bond length and bond energy and so forth. Okay, so if we want to solve this over and over and over, we need to put our whole program in a loop. So I'm going to drag a for loop over the whole program. And I'm going to make a button here. I'm going to go to Boolean OK button. I'm going to call it scan. I'm going to make the button say scan. I'm just going to turn off the label. There we go. Okay, and what is that button going to do? A couple things. We want to be able to switch between the scan mode and our normal operation. And so I'm going to make a case structure. When the button is not depressed, that's the false case. And when it's not depressed, I want this loop to run just one time. Because that's the same as how the program works now. It calculates everything once. But if the button is pressed, I will change it to be some large number. We could make this an input if we wanted to, but 2,000 points should be enough to scan over the potential energy surface with a reasonable resolution. The other thing we need to do is, normally, what is it we want to change every time we scan here? Well, we're going to be changing x max. So I'm going to make another case structure, and in the false case, the way our program normally works, I'm just going to use these same controls. And then in the true case, x min is always going to be 0, because that's how we've kind of defined it for the molecule. Is one of our nuclear positions is always 0. But x max, we want it to change. So I'm going to have to relate that to the loop iteration number I, because this increments every time the loop runs, so it's the only thing that is changing. So we want to, pick some angstrom step that will increase the bond length every iteration. So something like 5 thousandths of an angstrom should be reasonably small. And I also want to add a shift here, because there's really no reason to bother calculating bond lengths shorter than about half an angstrom, because it tends to be in the sort of infinite energy mode where the nuclei are too close to each other. So we can adjust that if it's unreasonable, but I think that should work. And I'm going to just move things over a little bit. This we want to put into the case structure. Yeah, just organizing so I know where everything is going. Okay. This number will be our new x max. X max will change every time, so it'll move the nuclei farther apart. And we want to calculate the energy at each position there. Okay. And then what we want to do at the end is we want to plot our potential energy surface, which will be this bond distance that we just calculated based on I. And our eigenvalue, which is our energy. We want to see how that's changing every time. And so I'm going to bundle our x and y values for that together. We're going to need a new xy graph on the front panel. And we need to add a case structure around this as well, because otherwise what will happen is we'll press the button, it'll scan, it'll write our potential energy surface, but then the program will turn back into normal mode, and then it'll just write a single point to this, and it'll overwrite it, and we want it to stay there. So I'm going to put that in a case structure as well, with nothing in the false case, and in the true case we'll wire up our button once again. Yeah, it takes a while to scroll over here. I think there is a button you can press to scan this, to scroll over the screen here, but there we go. Okay, I think that's everything, so let's test it out. And if it's not, we'll fix it. So since we're scanning, we want to put in a smaller number of points than usual, just to make it go a little bit faster. And the small fractions of a wave number that we might not be converging to isn't so critical, as long as we get the shape of the potential right. So let's scan, see what happens. You can see the bond length is increasing. Cool, the energy goes down. That was probably the minimum there. Now it's going back up again. And it's continuing to go out. We want it to scan until at least these wave functions stop overlapping, and thus the bond is more or less broken, which will also be the point where this energy stops changing. And no, it's riveting to watch here. See, your energy is still increasing. And the interaction between the two nuclei is actually, there is some effect at much longer distances than you would expect. But on the scale of the bond, it's approaching an asymptotic value. Okay, it's done. And here we go. Here's that potential we just saved. Note it's staying here. It's not overwriting itself or anything, even though the program's still running. And our program still works. I can change the potential we're solving for and resolve the equation, but our potential we just scanned is going to stay down here until we scan a new one. So this was H2+, because I used +1 charge for each nucleus. 0 here is still the ionization energy of one hydrogen atom. This asymptote is the energy of the electron being on one hydrogen atom or the other. This will be the same energy as would be, having the electron in the 1s orbital of the hydrogen atom. And a couple things you can learn from this. The bond distance here, where the energy is minimized, that is the equilibrium bond distance of that molecule. So this is like 1.4 or something like that, angstroms. Not unreasonable. And the bond energy is the difference in energy between the asymptote and the bottom of that potential. So that's how much energy you gain by making the bond. One thing to keep in mind is our program is only solving Schrodinger's equation in one dimension, which is sufficient for calculating atomic energy levels because it's spherically symmetric. For a molecule, however, the electrons are overlapping in more than one dimension. So this is not the actual potential energy curve of H2+. But this is how you would calculate it if we had included the other 3 dimensions here. This is how you would calculate potential energy surfaces and even potential in professional ab initio quantum mechanics software. Is you solve Schrodinger's equation for particular positions of all the nuclei, move them a bit, solve it again, move them a bit, solve it again, and plot the energy at each step. Then from this potential, you could calculate things like the vibrational bond frequencies and so forth, which we will actually do in the next video. So that's it for now.